You got it? I'll be with a prayer. Heavenly Father, we thank you again, Lord, for this opportunity we have just to meet together and study Calculus 2. Just pray for these students that they would do the best each day, Lord, for your glory. We just pray, help us to use this time wisely, just to, again, Lord, glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. All right, so first of all, I'm going to set myself a reminder to stop yammering on here at some point. Although I guess you guys would probably tell me, wouldn't you? So if I'm making a fool of myself, you'll let me keep going, huh? Yeah, all right. So if you look on the planner, at this point, we have come to the, oh man, the one day I didn't bring my silly rag. I've got, the board's kind of a mess. Oh well. I have geometry and applications to geometry and physics for today, and I'll do that. But first I'll just ask if there are any questions about your homework. So I don't have much in the way of homework on geometry and physics, right? So what I'll do is I'll work some examples in class. You'll be responsible for those. And also, I'll put a few problems on the quiz to be representative of the kind of thing I want you to know how to do. So there's problems in the book somewhere on these things, but that's not really the point. So again, are there any questions in particular? All right. Well, so what I want to talk to you about now is just kind of a general idea, which is the infinitesimal method. And so basically the infinitesimal method in a nutshell is this. We can take continuous sums via integration. All right, so I guess the first, most basic example of that I have is just the problem of area, right? If I have something like this is one curve, right, and this is another curve, and the top is y equals f of x, and the bottom is y equals g of x, right? You guys know the drill. If you know the intersection points are A and B, what do we do? Well, what I do is I envision a typical infinitesimal rectangle. Something like this, and I ask myself the question, what's the area? What's the area of this? Well, that's easy. dA, the little bit of area in this little strip, well, the width of the strip is what? It's dx, right? So dA is going to be, and what's the height of this strip? So h dx is clearly the area, but what's h? H is f of x minus g of x, right? In my current setup. And you can do that for each x from 0 to a, from a to b, right? So this gives me the area of the typical approximating rectangle, and then to find the total area, what do I do? Integrate dA, right? And of course this, I just wrote integral of dA as sort of a heuristic device to say what I'm really going to do is integrate from a to b of f of x minus g of x dx. So the area problem is an example of the infinitesimal method. We calculate the area of some fundamental infinitesimal thing, and then we take a continuous sum, the integral, to add up all the little bits of dA. So my first example, area. The second example I'll give you guys, and I'm not even doing a real example there with actual formulas and stuff, because you've done this already, and we don't need to belabor that. All right? But this one maybe you haven't done, arc length. Right? So suppose you've got a curve like this, all right? Whatever. And I suppose at the moment we're supposed to think about functions. So I'll say y equals f of x. And it's going from, say, point x equals to a over here to x equals to b. What's the length of this curve? So what I do is I think about what's the length of a little, and you know, I can't do it. I can't bear it. I have to talk parametrically to you guys. I guess I'm not supposed to, but I really want to.
Why not? Do it.
Do it. All right, so parametrically we have x equals to t, and we have y is equal to f of t for a less than or equal to t less than or equal to b. So like this is my x formula, this is my y formula. I'm just presenting this graph as a parametrized curve. And so if I think about a little tiny bit here, like a little, let me just blow that up, all right? So this little bit right here, well, you know what the length of that infinitesimal, imagine that that's much, much smaller, and here's a blow up of it. So this, you know how to calculate the little, a little bit of arc length here. We use S for arc length. You just do delta x, right? And delta y. And what's the relation between delta x, delta y, and delta s? I mean, you guys know. Delta s is the square root of delta x squared, right? Plus delta y squared. Which symbol?
X equals the
T? Oh, T. If that's better. You never learned cursive. Yeah, I know they're phasing it out of schools these days.
That's sad, though.
There are many sad things in this world. Let's see here. But what difference does it make? Yeah, somebody said that. What difference does it make? So here's a thing we could do. If you use your imagination, you could factor out a delta t, right? So suppose that you're going from time t here over to the next point at t plus delta t. So as time goes on, you go along the curve, right? Now, so what would this be infinitesimally? I could have written it this way. ds is just equal to, the square root of dx dt squared plus dy dt squared dt. I suppose if I was being more true to the infinitesimal method, I really should have just drawn something like this and gone, okay, so if you look at from here to here, this is ds, right? And so this right here would be your dx, and this would be your dy, and ds squared is equal to dx squared plus dy squared. And then you just take that and you divide by dt squared, and you multiply by d squared, that's multiplying by 1. Take the square root of both sides, voila. That's not a bad mnemonic to remember this by, if nothing else. Now, if there were a mathematician here, probably he would criticize that this is all nonsense because what I'm doing here is really just providing you a justification, perhaps, of the definition of arc length of a curve. Admittedly, that's true. Anyway, how do you calculate the arc length? We're almost there. Can you guys tell me? We figured out this is like the little bit of arc length. So if I want the whole arc length,
Integral.
right, I integrate ds. And okay, we're just looking at. I mean, I've taken a parametric viewpoint because I think it's more natural to derive these things parametrically. But okay, let me go back to the world of functions, which is all we know at the moment. And what's dx dt? So we had x equals to t, y equals to f of t. So like dx dt is 1, and dy dt is just f prime of t, right? So I can do the square root integral from t equals a to t equals b, 1 plus dy dt squared dt. Did I put a t up here? I meant b, sorry. Or if you want me to make it all nice and where we are at the moment, as opposed to the end, at the end of the course, we talk about parametrized curves, all right? So let me do it there. For the moment, I really should have just told you this. There it is. That's the formula for arc length of a graph from A to B. Since I've said this much, I will tell you for a parametrized curve, the formula is just this. The integral from parameter 1 to parameter 2 of the square root of dx dt squared plus dy dt squared dt. That would calculate the arc length of a parametrized curve. One more example, and then I'll stop talking about parametrized curves for about a month or two. Since we've gone this far, I'll do it. X equals to r cosine t, y equals to r sine t. So dx dt is what? Dy dt is what? And let's say 0 less than or equal to t less than or equal to 2 pi. Calculate the arc length. So these are, by the way, the parametric equations of a what? It's pretty easy for you guys to, a what? A circle, right. If you look at these, you can see that x squared plus y squared is equal to r squared. So in fact, these are the parametric equations for a circle, and we're calculating the arc length of a circle right now. What happens under the square root there? You've got r squared sine squared, right? R squared cosine squared. Sine squared plus cosine squared is what? 1. So this is actually just the integral of r, 2 pi dt, also known as RT, evaluated from 0 to 2 pi. There you go, 2 pi r. So there's the circumference of a circle from calculus. It's not that hard, really. What's up? Yeah? Let me look up another example here for a second. I can't just go willy-nilly calculate the arc length of anything. Actually, let me do it. You guys, give me any function you want. Let's calculate the arc length of it.
Don't you have to square the radius?
Hmm?
Don't you have to square the radius?
I do. I did. And then I unsquared it. Why?
Why? Oh.
It's a square root. Yes, the natural enemy of the square. Let's see here. Okay, so that's there.
End up with 2r.
Hmm? How did I end up with 2 pi r?
You end up with r squared sine squared plus r squared cosine squared. So, no, never mind. No, you're fine.
Okay. Okay. Give me function, any function. What do you want? F of x equals 2, you pick it.
Cosine.
I heard x squared, I heard cosine, I'll put them together. There you go. All right, and let's say for 0, let's say for 3 less than or equal to x less than or equal to 1,000,000. There we go. Calculate the arc length. Actually, let's not calculate the arc length. Let us set up an integral whose value is the arc length. Let's find what's called an integral solution to this problem. Somebody tells you to find an integral solution to a problem, you should be very happy. That means you just have to set up the integral. You don't actually have to do the integral. These are precious and wonderful words. You should pay attention to them. So here we go. What's f prime of x? You got yourself 2x cosine x, right? Minus x squared sine x. And so the arc length, by the discussion we just had, or if you're a mathematician by definition, 3 to 1,000,000. Why did I do 1,000,000? I don't know what's wrong with me. Anyway, it's done. Square root of 1, all right, because we've got a graph, so we do 1 plus dy dx squared. Dy dx in this case is 2x cosine x minus x squared sine x, close parentheses, quantity squared, close square root dx. There you go. That is an integral solution to this problem. That integral is the arc length. I am not confident I could actually do that integral using the techniques we know in here. However, we could calculate it approximately using the techniques we talked about yesterday, right? You could use Simpson's rule, you could use trapezoid rule. I'm not going to do it, but you could. All right. What are other applications of the infinitesimal method? How about, what do you guys want to talk about? Volume? Sure. Talk about volume. So for example, I could calculate the volume of a pyramid. Right? Suppose the pyramid has height. So it's hard for me to, if you can imagine the height of it being h, it's better if I kind of draw it like, this is just a forward view. So you can imagine it kind of going back into the board here. This is the height h, okay? So what's the volume of a pyramid of height h in base A, let's say? So that A is here too. So what we do is we slice it. And the slice I will take is a square slice. Don't get too carried away in my picture here. It's easier for me to draw the slice down here. That's just the, let's say that's this right here, okay? And so that typical slice has a particular side length. What do you want to call it? How about L? Right? And I need to say, okay, how long is L? How long is L? Well, it's not negative, it's a length, right? Between 0 and A, right? So we need to invent something else in order to understand this. How about Z? So, or if you like Y, what do you guys want, Y or Z? It's up to you. Z, all right, Z. So the thickness of this little slice is dz, all right? And so the volume of this slab is going to be L squared, because that's the area, times dz. Does that make sense? Now the problem is, L is not a constant, right? So before we can do the integration, we have to understand how L relates to Z. I claim it's geometrically clear that L has to be linearly related to Z in the following sense. Like, L has to be a function of Z, so L has to be something like mz plus b for some choice of these constants, right? If you don't like this way, you could draw there's similar triangles you could draw to convince yourself of the same thing, but I personally prefer this approach. Now we have some data. We know L of 0 is what? We know L of h is equal to what? L of 0 is a. That's also equal to m times 0 plus b. So therefore b is in fact equal to a. And L of h is what? 0, but that's equal to m times h. We just figured out that b was a, right? So I'll write a here. So therefore m is equal to minus a over h. There you have it. L is in fact equal to minus a over h times z plus a. All right? And we can double check that. What happens when you put in z equal to 0? Put z equal to 0, we get a. Good. If we put z equal to h, what do we get? L equal to 0, right? So the formula checks. We should always check formulas like this when we make them up. All right, so now we can integrate v, the volume, the integral, from z to z equals what? Z equals 0 to h of, here we go, a minus az over h quantity squared dz. I would recommend not foiling that out. Like for me, a u substitution is really helpful here. Actually, you know what I'm going to do? I'm going to make an L substitution. So this is the integral of L squared, and then I've got dl times what? So dl is actually equal to minus h, well, I mean dz is minus h dl over a, right? And you already know what is L of 0. A, right? So this bound is a. And what's L of h? 0. So this gives us minus, well, I'm gonna flip the bounds if you guys don't mind. So I get h over a integral from 0 to L, excuse me, 0 to a of L squared dl. So in other words, h over a, L cubed over 3 evaluated from 0 to a, and there you go. Here's the well-known formula. So I get h over a times a cubed over 3, or if you like, 1/3 h a squared. Perhaps you already know that that's the formula for the volume of a square pyramid, height h, base side a. This can also, of course, be derived from various slicing and dicing, rearranging of the pyramid geometric arguments, right? It's a pretty simple shape, so there's like other ways to, you could, if you were a sufficiently clever 5th grader, you could do this without calculus, right? But I said sufficiently clever 5th grader. I did qualify that. There are lots of 25th graders who can't do this, with or without calculus. So, you know, whatever. But once you do this, if you understand, you can easily do a pentagonal pyramid, or a tetrahedron, or whatever else. But then the problem with the problem with something like this, right? And so forth, right? Is when you take the slice, you got to figure out what. Yeah, well, you could still say that the distance is L, and L is like linear. I mean, there's still if it's got flat sides, there should be some linear relationship between the characteristic side length and the the height off the base. But the trickier thing is then you got to figure out, I'm not drawing this very well, but this was supposed to be a regular polygon. Sorry, it didn't go well. Let me try this again. Here is approximately a pentagon. So if this is the side length is L, what's the area of a pentagon? Go. What's that? You don't know? You guys don't remember the area of pentagon formula? Exactly, right? So you'd actually have to work out what is the area of a pentagon to do that problem. Yeah.
Can you show how you related L and Z with the triangle?
Oh, you want the similar triangle? Sure. Let's see here. If you... I think if we look at the... Let's see here. How can I say this? I think with this... If you look at this, like the projection of this face into the vertical plane, you know, in that projection, it doesn't change. The projection into the vertical plane here, the vertical plane that goes through the apex of the pyramid, it does not change horizontal lengths. It changes like depths. It skews depths, but it doesn't skew the horizontal lengths. So if you look at that, you've got this. The height is h, right? Well, the whole thing is h, and this down here is a over 2. Well, I guess, I'm sorry, more to the point. There's this triangle. Down here you have a, and you have height h, right? But you can also look at let's see here. Are you actually asking me why this formula is true, or are you asking me for a different solution?
Yeah,
Why this is true. So you don't really want me to show me, you don't want me to show you the other solution, do you? I mean, you can draw two triangles here like this. And they're similar triangles. So, but the annoying thing is the red triangle, which is this green triangle up here. So that triangle is similar to the black triangle. And the green triangle, right, it would have, this distance would be what? It wouldn't be z, because z is down here. This would be h minus z. So you see h minus z over L, which is this distance, is the same as, to h over a. That's the similar triangle way of deriving the relation between L and z and h. I'm not a fan of that because I can't always see the similar triangles when I'm working problems, but I can personally much more successful no matter my level of sleepiness doing this. Here is just an observation that the length of the side has to be linearly related to the height off the bottom because it's got flat sides. There's some kind of angle that relates them, which is a constant. You give me there's a sine or a cosine tangent, whatever, I don't really care. And that's why I have this kind of formula, and then I just have to figure out what the m and the b are. So you can either search for unknown m and b to find the relation between, I mean, you're looking for some function that is linear, that is equal to a when you put z equal to 0, and is equal to 0 when you put z equal to h. How do you find it? Yeah.
I have a question about that. How does L of h equal 0?
Because that's the assumption of the problem, is that this is when you have z equals to h, you're up here.
Yeah.
It's given.
Oh, okay.
I mean, z equals to h is the top of the pyramid. It's,
And then L is 0.
yeah. So these two equalities right here, these are given from what's the nature, I mean, the setup of the problem once you've defined what z is.
Yeah, I think I was overthinking.
Yeah. Do you guys ever figure out what the area of a pentagon is, though? It's fun to figure it out. But I probably shouldn't do that right now. I should probably go on. You can do that, though. Oh, we don't have the necessary. I actually need L'Hopital's rule to finish this. If you keep going with this, right? If you take the limit, if you keep going and going and going and getting larger and larger n, what do you get to eventually? A circle, right? So if you take the limit as the number of sides goes to infinity of the perimeter of an n-gon, you'll get 2 pi r. That assumes, of course, that the this radius is fixed in that limit. Let me get back on track, though. Let's see here. What's our next example? We've also had some homework on like solids of revolution, right? There are other ways of calculating volumes. We had like you have the solids of revolution. You have the shell method or the washer method, right? So I'll do one more on volume for you. Suppose we calculate the volume of a pretty standard example. Let's look at y equals x and y equals x squared. Rotate around, let's say, the y equals, x-axis, excuse me, y-axis. So this will bound a certain area, all right? So here it is, y equals x is what? This, right? Y equals x squared, this guy. What are these points? So we have points of intersection, either 0 or 1, right? And you're taking this and you're rotating it around the y-axis. So that gets us over to here like this, right? And I want to find the volume. I guess I can hazard a picture down here. It's something like, it's hard for me to draw this thing worth anything. Roughly like that. It's like a bowl with flat insides, right? Like a conical inside. If you could imagine taking, it's like maybe like half of a watermelon, like the regular curvy side of the watermelon, and then you just like take a conical drill and drain into the middle of it. I don't know. Sorry. What's that?
Grinder.
A coffee grinder? Oh. Yeah, there you go. Sure, why not? So to calculate the volume, again, slice and dice. So what we do is we imagine finding an infinitesimal, again, that's my theme here, guys, is that we chop it into infinitesimal, in this case, washers, right? So up here, that looks like just this. Right, and we want to figure out what's the bit of volume here. What's the infinitesimal volume of this washer? The infinitesimal volume of the washer, well, looks like the thickness isn't dx this time, is it? What is it? It's dy. And so I also need to figure out what's the inner radius, right? And what's the outer radius, right? So for this, I want the right x minus the left x. I'm sorry, still not right. Excuse me. Excuse me. I need to draw a little bit more here before I'm jumping the gun here. I need to draw another picture. So if I take this thing and draw it in a way which is better, like this maybe, let me just set it vertically. What's the area of this? So here is R in, here is R out. The area of this is, what's that?
R out minus
Yeah, pi R out squared is the area of the big circle. And then I have to remove the area of the inside circle, right? So I take pi R out squared minus pi R in squared, and that gives me the area, right? But what's dV? Well, dV is pi times the area. Excuse me, it's the area times what? It's the area times the thickness. That gives me the volume. The thickness is dy, so area times dy gives me a little bit of volume. Now, but what is the area? It's pi R out squared minus R in squared. So what is that though? I mean, more specifically, pi times the right x minus the left x squared. I mean, I say that there's a right function, like this is the left x, right? This is the right x. Does that make sense as terminology? There's one on the right, there's one on the left. Right? I mean, correct? So what? You might ask, what difference does it make? It's your prerogative. Some of us have to answer these questions. If you choose wrong, you'll get a negative, right? But here, XL is this, x equals to y. So XL is y. The right x, on the other hand, square root of y. Now, how do I know I need functions of y? Of course, I actually don't need xr. I need what? I need xr squared, right? So put those over here, we get pi y minus y squared dy. And what does y range over here? Here's 0 down here, right? This point up here is 1, 1 actually, right? So that. So the volume of this solid of revolution should be given to me by integrating, adding up the volume of all these little washers from 0 all the way up to 1. Does that make sense? If you guys had Calc 1 here, I know you've seen this before, but if you haven't, you might not have. That's why I'm going over it. All right? So let's see here. Long story short, volume. Integral of dV, in this case, integral from 0 to 1 of pi y minus y squared dy, also known as pi times 1/2 minus 1/3, aka pi over 6. Integral of y is 1/2 y squared. Integral of y squared is 1 y cubed. 0 to 1 gives you 1/2 and 1/3. I mean, it's just that. Okay, so any questions before I go on to my next example here?
Oh, no, so that was the volume of the whole thing.
Yep.
Okay.
Shall I try a trickier example? Now, there are a few other applications that we have left to go. I'll do another volume. I'm going to probably stick with volume for today, but tomorrow I should probably do surface area and maybe an example or two, maybe on work or force on a dam. So this is a torus. Let's see here. Oh, not quite right. So here I want to think about a torus that has, let's say, this radius being, let's say, r, and I'll let the typical circle be radius, let's say, a. So I want to calculate the volume of this torus.
So the radius of that circle thing?
Yeah, so I mean, here's a more precise way of characterizing this volume is it's a volume of revolution, right? It's a volume of revolution. What volume of revolution is it? Well, we're just taking a circle, right? Out here. The circle's at r, right? And the radius of that circle, by what's given, is what? Is a. And I'm just saying, take that circle and rotate it all the way around and back in through the board and back around. That gives you a torus, right? It's just a circle. Yeah, donut if you like. So this one, what I'm going to do, instead of using washers this time, I'm going to use shells. All right, the method of shells says to take the volume and slice it into like cylindrical shells in this case. So what that means, I mean, we did square slices on the pyramid, right? We did these like little pineapple slices or whatever you want to call them on this, right? And now I'm suggesting that we use cylindrical shells. So cylindrical shells are going to look something like this on my picture here. Now, I'll try. I'm going to try, but it's going to look awful, but I'm going to try. Up here, that's something like this. And it's like, I probably can't draw it worth anything, but if you can imagine just taking a slice. If I draw the donut from the top view, all right, the cylindrical shell looks something like, I tried. That was supposed to be a circle. It's getting worse. So here's the cylindrical shell from the top. Sad. Oh well. This is not bad though. Anyway, so the point is we need to figure out what's the volume of the cylindrical shell. Now, first of all, the cylindrical shell, we can find it where? We find it at position x, right? Coordinate x. What's the equation of this guy right here? You can solve, we've got x minus r quantity squared, bless you, plus y squared equals to what? This is a circle centered at r comma 0, radius a. So we do x minus r squared plus y squared equals a squared. And you can solve that for y. So this has equation y equals to the square root of a squared minus parentheses x minus r quantity squared. That's y as a function of x. Now, not for the whole circle. That's just legitimate for this part, right? What's the volume of this cylindrical shell? So if you think about a cylindrical shell, just in the abstract, it's something like this. So for me, the thickness is just going to be dx, So the thickness is dx. And if you took this and you just laid it out flat, right? If you can imagine unwrapping the cylinder as just a rectangular slab, the thickness would be dx, right? This is the height h, all right? Now the height is actually what? We can write that as 2 times y for the one we're interested in, which is in fact twice the square root of a squared minus quantity x minus r squared. And what's the length? You take it, you lay it flat. What's the length? 2 pi x, right. It's the circumference of the circle. So the volume, dV, is, of course, nothing more than 2 pi x times 2y, because that's my height, times my thickness, which is dx. But what's that? That's 4 pi x is the square root of a squared minus quantity x minus r squared dx. There's your volume. Not your volume, that's your infinitesimal volume. That's the volume of a typical approximating cylinder. Infinitesimal cylinder, fine. Shell. Cylindrical shell, I should say. Not cylinder, it's a cylindrical shell. Now what? What range of x do we do this for? For x from what to what? We have to ask this question every time we do one of these, is what's the appropriate range of the integration variable? R what? R minus a over here plus a. So this is for r minus a less than or equal to x less than or equal to r plus a. Now, you might say, well, I don't see why you used cylindrical shells here. You could have used washers, right? You could slice the donut up into a bunch of, like, you could imagine sort of slicing the donut up into a bunch of pineapple rings stacked on the top of each other, sort of, you know? Like, you could chop it that way. Chop, 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 chop. You could do that. That's true. That's another way you could calculate the volume of the donut, of the torus. If you do it that way, you get a different integral. I think if you do it that way, you get an integral where you have to do trig substitution. I don't think we have to do trig substitution on this one, though. I could be wrong. Oh, I think I'm wrong. Uh-oh. V. So here we go. Off to the races. R minus a to r plus a. Ooh, this one looks like fun. 4 pi x is the square root of a squared minus parentheses x minus r squared. This is the first example I've done today where we really need the integral techniques that we've developed this semester. How should we do this integral? What kind of technique should we use? I heard an x minus r equals to a secant theta. I think that's going to be a good idea, because then I've got a squared minus x minus r squared is equal to what? 1 minus secant squared theta, which is a squared tangent squared theta. Woohoo!
Wouldn't it be cosine because it's negative? A squared minus x squared, that's squared.
Ah!
Cosine.
Silence! We're in the middle of something. Oh! You think I should use... Yeah, maybe you're right. Oh, I'm sorry. I think you tricked me. You tricked me. Yeah, we should use cosine. Thank you. Or sine. Sine's even easier. Let's use sine. If we do that, this is cosine squared theta. And so if we have r... sorry. What what do the bounds change to? If we have x equals to r plus a, that says that x minus r is equal to a. So a is equal to a sine theta, so theta is equal to? So we got ourselves a pi over 2 and a minus pi over 2 for our bounds. So we got ourselves 4 pi. What's x equal to? X is what? X is r plus a sine theta, because I solve for x. The square root simplifies to a cosine theta. The dx is another a cosine theta d theta. And so we have the integral from minus pi over 2 to pi over 2 of 4 pi times r ra squared cosine squared theta plus a cubed cosine squared theta sine theta d theta. Which we can do. This is an integral we can do. Thinking about the cosine squared, that gives me a 1/2 1 plus cosine 2 theta. That integrates to sine 2 theta. But sine 2 theta at plus or minus pi over 2 is either sine of pi or sine of minus pi. So this piece, it doesn't integrate to 0, but only the 1/2 comes to anything. So basically this ends up integrating to theta over 2, evaluated from minus pi over 2 to pi over 2. And so that, of course, gives you pi. This piece ends up integrating to 0, and you're just left with 4 pi squared r a squared. Or in other words, 2 pi r times 2 pi a. What's that? Excuse me, pi a squared. I'm sorry? Yeah, it's a second here. Let me think about that. Pi over 2. Oh, it should be pi over 2. Yeah, that's good. But I still got this 4. So 4 times that gives me, you're right, I'm not right yet. So 4 pi times pi over 2 gives me 2 pi. And if you check it, we got 2 pi r times pi a squared. You'll have to work it out. You can work this out. This integrates to 0. I know we're out of time, so I'll stop, but that is in fact the answer. It's the most natural thing you could expect. It really is. It's just the circumference of the big circle times the area of the typical cross section. So if you could somehow slice the donut and just lay it out as a tube, it would be the area, it'd be the volume of that cylinder. So I don't know, it doesn't have, I mean, it's really nice that it works out that way, but that's how you can actually calculate it. Anyway, if you guys have questions about your homework, you can ask tomorrow. I keep asking if you have questions, but if you don't ask questions, then I'm not going to answer them. Just saying.